All right, let's get started. Good morning. Wow, for Friday, that's not so bad. Okay, good. Okay, so we're nearing the end of this Relay for Life Fund Drive. This is the last class that I'll be showing that. So we are not quite there yet. You've got a little bit of work to do. Again, if you have a spare change you want to give to Relay for Life, please do. It's a wonderful cause. All the money goes to Relay for Life for cancer research, looking for cancer treatment, prevention, and ultimately a cure. Okay? And if we're a little bit short, I'll put in something to push us over, but you gotta get it close to give me a chance to do that. All right? Okay, so today we'll look at 4.3, section 4.3. We're still going to be looking at how derivatives and shapes of the graphs are affected. There's a lot of stuff going on in this section. We'll look at just part of it today, and then we'll continue that section on Monday. I want to start by sketching a graph, pretty simple graph. And sketch kind of big in your notes. We're going to be adding stuff to it. I want this to look essentially like a sine graph. Something like that. And for simplicity, we'll make these 1, 2, 3, and 4. Okay, so the graph goes up and down. On certain sections of this, parts of this graph, the graph is increasing. For example, from 0 to 1. Every point as you move to the right gets higher and higher. So this section right here, this is what's called an increasing interval. As we move to the right, each point we encounter gets higher and higher, and we call that an increasing interval. Notice the same thing happens at 3 to 4, right? We start pretty low, but each time we move to the right, every point on the right is somewhat higher than the previous point. So this is also another increasing interval. The middle portion here, from 1 to 3, we have the opposite. So this portion, this is a decreasing interval. Every point to the right of the point that you have chosen as you move to the right gets lower and lower. That's a decreasing interval. So we found out that we have an increasing. I'll abbreviate increasing with just by INC from this point on. The intervals are 0 to 1 and 3 to 4. Okay? And the decreasing interval we have is 1 to 3. Okay, so that's not very difficult to grasp. Now the thing we want to tie to the increasing and decreasing part of the graph is how they are affected by the derivative. Let's go to an increasing interval right here. Let's say between 0 and 1. Notice that it doesn't matter which point I choose. If I just choose a random point there and sketch the tangent line on that point. Notice that anywhere on an increasing interval, the tangent line would have a positive slope. Same thing here. If I go to an increasing interval, anywhere I go, I sketch a graph, a tangent line, it'll have a positive slope. I'll write that down here. F prime is positive. Remember, that means tangent line slope is positive. Conversely, if you go to the decreasing interval from 1 to 3 here, pick any point you want, right here, let's say, or any other point, I don't know, right here. Doesn't matter where you go, you're always going to see a negative tangent line slope. So we notice that on a decreasing interval, f prime is less than 0. That means the tangent line slope is negative. Okay? So that's what we notice right here. The sign of the derivative on an interval will tell me whether the graph is increasing or decreasing. Conversely, if I can see the graph, then I can look at the shape of it and determine what the sign of the derivative would be on an interval that I have chosen. Okay, let's make a couple other observations. At x is equal to 1, there is a relative, sometimes called a local maximum. Right? X is equal to 1, we're at the top of that hill there. That's the highest point in the neighborhood. It could also happen to be an absolute max, but it is definitely a relative maximum. It is higher than all the points nearby that in the region. Notice the sign of f prime before you reach that and after you have left a point. Notice it is positive before reaching it, the local max. And negative after. Right? Everyone see that? Think about it when you're climbing a mountain. You have to climb uphill before you reach the peak. And after you reach the peak, you go downhill to come back down to ground level. If someone blindfolds you as you go up the mountain, you can still feel that. Your body can tell you we're going uphill. And at some point, if you feel like you're going back downhill again, you know you've reached the maximum at some point. So we have to have a positive slope before and a negative slope after. At x is equal to 3, we have the opposite situation. There's a local minimum, and f prime is negative before and positive after. And so this is one of the most important results from derivatives so far. Just by looking at how the derivative changes sign before and after a place where f prime is 0, we can tell whether we have a maximum or a minimum. So that idea forms the basis of what's called the first derivative test. The first derivative test is what you would use to find the maximum or the minimum of a function. So this is for finding local max / min of a function. Okay, so what does this say? First, we got to find out where they might be. So we look for where the tangent line is horizontal or undefined, like we've covered before. So let's say it this way. If C is a critical number, which means, remember, f prime of C is equal to 0, or f prime of C does not exist. Okay, so on the graph I drew on the last page, it would be at x is equal to 1 and x is equal to 3. We have those two locations with flat tangent lines. Once we found them, we check what happens before and after each one of them. If f prime of x changes from positive to negative, then that's a situation we have at x is equal to 1. We have a local maximum at x is equal to c. Right? We look for the sign change. You're climbing the mountain before, you're going downhill afterwards. You've reached the max at some point. If f prime of x changes from negative to positive, then we have a local or relative minimum at x is equal to c. If there's no sign change, then we have neither a local maximum or a minimum at x is equal to c. We have to see a sign change. Okay, so this is a very, very important result, and it's a very, very conceptually very simple result. We look at the sign change, increasing before, decreasing after. You must have reached the max at some point. Decreasing before, increasing after, you reach the bottom of a little valley at some point. It's a very simple idea, yet incredibly useful and powerful in finding maximum and minimum of something. Okay, let's try that on something. We'll start with a simple polynomial function here. One plus 3x squared minus 2x cubed. Okay, so let's find out on what intervals is this thing increasing, on what intervals is this thing decreasing. And once we know that, we actually automatically know where the local max and min can be. Once you know this, you know that automatically, just by looking at the sign change. All right, so we know we got to start by finding out where the critical numbers are. Those are potential locations of the maximum and minimum. So let's do that first. Gotta remember, critical numbers are where the function has a zero derivative or the derivative does not exist. Those are potential locations of local maximum and local minimum. This one has a very simple derivative, 6x minus 6x squared. This is a polynomial. It's defined for all values of x. So we're not expecting anything from that criterion. Only this is going to give us something. All right, so that's easy. Let's factor 6x out of that. So this tells me that x must be equal to 0 or x is equal to 1. So these are possible locations of a maximum or a minimum. There are also locations where the function is not increasing or decreasing. It's kind of halfway in between. It's not doing any kind of change. But once you move away from these two, we expect the function to be increasing or decreasing, one or the other. And one easy way to see what's going on here is to draw a number line. So this line right here, this represents all the possible values of x. And on here, I'll put down the critical numbers I found in increasing order. So I found 0 and I found 1. I'll put them here and here. Above this line here, I want to see the sign of f prime of x. Above this line. These places will have 0, no signs, right? But once you move away from them, we expect something different to happen. Okay, so the way you check for these things here is you look at this interval. What you want to do is to choose any number to the left of 0, meaning less than 0. Choose any number and check the sign of f prime. And you can choose any number that is convenient for you to choose. Here, let's just make it simple. Let's check f prime of minus 1. Why not? But there's nothing wrong with minus 10 or minus e or minus pi if you feel like doing that. Whatever you do, we want to see the sign. Here's f prime of x. I want to put in minus 1 for x. And so I get negative 6 minus 6. I don't care about the number. All I care about the fact is the fact that it's negative. This means that any number you choose here is going to give you a negative sign. So I'm going to fill up the interval above with a bunch of negative signs. Okay, does it make sense what I did there? Everyone? Yeah. Oh, it never ends, right? Yeah, in that case, we know the fact that it repeats. So if we can find out the behavior between any two neighboring ones, we know that's going to repeat down the road either way. Yeah. That's a little bit too complicated for now. We'll eventually deal with a situation like that, but just not yet. Okay, now we check out between 0 and 1. Here again, we choose any number. Let me make this more clear. Choose any number less than 0, right? Not any number, but choose any number less than 0 for that. Here we choose any number between 0 and 1. And then check sign of f prime. Any number is good, just not 0 and not 1. Anything in between is entirely fine. So I'm going to choose 1/2. Then we go back to f prime. We check the slope. The first number is obviously bigger than the other number. So this is going to be a positive number. Again, the number is irrelevant as far as what we're concerned about why we're doing this. The number is irrelevant. All we want to see is the sign. That's a positive number, indicating that any number you've chosen in that interval is going to give you a bunch of positive signs. So I filled it up with a bunch of negative. Here, same idea. You choose any number bigger than 1. To the right of 1 means bigger than 1. Check the sign. So we get 6 times 1 minus 6 times... No, I can't do 1. 2. 2 will do. You cannot choose 1. You got to go something bigger than that. And we get, that's clearly a negative number. That's all I care about it. Negative, negative, negative. Negative, remember, negative derivative means the function is decreasing. We expect the function to be going down like that. I'll put an arrow there to remind me what's going on. Positive means increasing. The function is going to be going up as we move from left to right. Decreasing again. So just by doing that, notice that I already get a pretty rough idea of what the function might look like. I expect it to go down, go up, and go down. Exactly. Thank you. Exactly how low it gets and how high it gets, that's something we have to find out by doing a little bit more. But we know what it's doing, down, up, and down. And then just by looking at that, I see the sign change. Decreasing before, increasing after, there is a local minimum here. Increasing before, decreasing after, there is a local maximum right here. And I'll write that down. See a local maximum at x is equal to 1. Right? F prime is positive before, and f prime is negative after. And we have a local minimum at x is equal to 0. So it's negative before, positive after. I also see that the function is increasing on the interval 0 to 1. And the function is decreasing on two intervals, minus infinity to 0 and 1 to infinity. Okay? Any question on this example? Yeah. For this one, I don't think it's that big a difference. But you're right, there could be functions where the factor out of form might be easier to deal with. It depends on what you're dealing with. We'll see an example that actually deals with that in a little bit. Okay? All right, before we move on, any question on what we just did? Good? Okay, let's do another one. 3x to the fourth minus 4x to the third. Want to do the same thing, find out the local max and min, increasing and decreasing of this thing. And maybe we can use that information to come up with a rough sketch. But if not, that's okay. Okay, so we know what to do. Find the derivative. Simple stuff here. Make that equal to 0, right? Let's factor out a 12x squared. So here we see that x has to be either 0 to make the entire thing 0, or x is equal to 1. So just by chance, we get the same two numbers. But of course, in general, these will be just numbers. Okay, so we found out where f prime is 0. Now we check left and right of each one of these, and we find out what's going on. We draw the line representing all the possible values of x. 0 here, 1 here. Do these in order of increasing order, small, large. Above the chart, we check the sign of f prime. Obviously, nothing's going on here. Okay, and just like before, we choose any number on these intervals. Choose whatever you want that's less than 0. I don't know, I'm going to choose minus e just because I can. Right? There's nothing wrong with that minus e. Now here, when we check the sign, occasionally we can actually take advantage of the factored form like Manuel pointed out. Notice that this part, this is always positive. 12x squared, whatever x is always positive. We know any number squared to even power is always positive. So the only thing that's going to affect the sign is this guy right here. I only have to look at what happens with the number I've chosen, minus 1. When I check the sign, f prime of minus e, my 12 minus e squared is always positive. I don't care. I know that's positive. What happens afterwards is what I care about. So that's clearly negative. So we're going to get a bunch of negative signs here. Function is decreasing at that interval, on that interval, going downward. What about between 0 and 1? What do you think? What sign do we get? Choose any number. How about 1/2? That's always positive. We ignore that. If I choose 1/2, 1/2 minus 1 is clearly negative. So that's going to be another decreasing interval. Continues going down. So it keeps going down, comes to a brief stop, and it keeps going down again. How about here? What do we get? Sign. Positive. Very simple. Any number you choose, that's positive. Any number bigger than 1, that's positive. Increasing thereafter. So this thing, where's my, there, goes up, right? Okay, now at 0 here, it is a critical number, but it is not a local max or minimum because we don't see a sign change. Decreasing before, stops briefly, decreasing again. That's like when you're going downstairs. Between floors, you reach the floor. You have to go around a little bit before you're going down again. So you go from third to the second, brief stop, second to first. This is not a local maximum or minimum. At x is equal to 0, no sign change in f prime. So it is not a local max or a minimum. What do we have at 1? Decreasing before, increasing after. You reach the minimum at some point, right? Local minimum. Now, sometimes you want to know what the actual function value is. So let's give it as a point. The minimum happens at x is equal to 1. And y is equal to 3 minus 4. So that's f of minus 1. This tells you where it happens and what the actual value of y is. This tells us that we expect nothing smaller than minus 1 near that region. As we move away, there might be something smaller, but near this region, that is the lowest point we can find. And this function right here has no local maximum, only has a local minimum. It is 1, sorry. Yoink, there, thank you. Right? At x is equal to 1, f at 1. You're right, my bad. Questions on this one? All right, let's do this next one. Along the same line, but a slight twist. Here we're going to start with a graph of f prime, not the function itself, the graph of f prime. I want this thing to do this. Okay, remember, this is a graph of f prime of x. We want to find increasing, decreasing intervals and locations of local max and min for f of x. All right? Oh, let me label these things. This is 0, this is 1. This occurs at halfway in between. This is 3 over 2. This is minus 1/2 for x. Going in intervals of 1/2. Okay, now be very, 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 very careful. We started with the graph of f prime, not the function of f. It exists, but we don't know what it looks like. But we know its derivative looks like this. We want to find out, based on this function here, can we see where the local max and min for the original function might be? This is actually very simple because we can use the information we have found here to draw the chart, the number line that we have been drawing. First, find out where f prime is 0. F prime is 0 at 0 and 1. We keep running into those numbers. But that's okay. Okay, so these are our local, well, not local, these are our critical numbers where f prime is equal to 0. Then we check what's going on between and to the either side of them. So here, instead of choosing numbers and plugging into derivative, we simply look at derivative and look for the sign. Remember, the number of f prime is irrelevant. Just the sign is all we care. Check out between 0 and 1. It is positive, right? So positive here. This thing is increasing. The original function is increasing. Even without sketching that, by looking at the information that the first derivative contains, we can make that determination. To the right of 1, function is always below the x-axis. F prime is always negative. So function is decreasing on that interval. Same thing here. It's always below, so it's negative. Decreasing again. Now, based on this chart, we do what we just have been doing on the last two examples. Looking at the chart, looking at how the signs are changing, we can find out where the local max and min can be. Based on this, we see that the local max for the function f of x, the original function, is at x is equal to 1, right? The increasing before, decreasing after. And the local minimum for the function f of x is at x is equal to 0. Decreasing before, increasing after. And the function itself will be increasing on the interval 0 to 1. And the function will be decreasing on the intervals minus infinity to 0, and then 1 to infinity. All right? Does that make sense? Any question on this one? Be very careful. We weren't asking about where the local max and min of the derivative are. Those we can spot just by looking at. We were looking for the local max and min of the original function that gave us this derivative. And from all we did is using the sign information from the derivative to make that, to draw this conclusion right here. Questions? Okay, now let's look briefly at what the second derivative tells us. The first derivative tells us when something is increasing and decreasing. Let's find out what the second derivative tells us. If you say f double prime is positive, then what this means is f prime is positive. What this means is that f prime is increasing. In other words, the slope of the tangent line is increasing. Say that again. Both of the signs of what? No, all this is saying is that f prime is increasing. Something prime is positive means something is increasing, regardless of what that thing itself is doing. Again, f prime is increasing. This is all it tells us. What f prime itself is doing is not contained in this information. Right? You can, okay, if they're both negative, then you can say that the slope of tangent line is negative at that point, and it's decreasing near that region. Well, if it's both negative, it has to get more and more negative, shallow, steeper and shallow. But you're getting too far ahead. All we're saying is that something prime is positive means something is increasing. That is all the thing we're looking at here. So what happens when you have this kind of thing going on is you will get a shape that resembles an upward opening parabola. Something like that. Notice what happens if I start by looking at the slope of the tangent line here. It's a large negative number. If I move over here, it becomes 0. If I move over here, it's positive. So it went from negative slope to a 0 slope and then to a positive slope. As I move from left to the right, the slope of the tangent line gets bigger. And that will result in a shape that looks like an upward opening parabola. We call this a concave upward shape. Okay, you see if you move left to right, it is getting bigger and bigger. And this means f double prime is positive. F double prime negative means f prime of prime is less than 0. So that means f prime is decreasing. That means the slope of tangent line is decreasing. And we'll get the opposite situation. We'll get something that resembles a parabola opening downward. And you can see that fits the description right here. On the left end of this, I have a positive slope. Over here, I have a 0 slope. So I went from a positive number to a 0. The number got smaller. As I keep moving, the slope becomes negative. So I start with a 2, maybe. I went to a 0, I went to a minus 3. It got smaller as I move from left to right. We call this a concave downward situation. And this implies that f double prime is less than 0. So think of concave as which way something that resembles a parabola may be opening, upward or downward. Upward is concave up, positive second derivative. Concave down opens down, negative second derivative. Sometimes you get a graph that has this kind of situation. Notice that on this portion right here, f double prime is negative, concave downward, right? And on this portion right here, it's concave upward. It resembles a parabola that opens upward. There is a switch between the two. We went from concave downward to concave upward, and the switch happens at this dot right here. This is called an inflection point. It's the location where f double prime changes sign. If you think about for something to change sign, there are two possibilities. It either becomes 0 at that point, or it becomes undefined at that point. So that's also where f double prime is equal to 0, or f double prime does not exist. That's the only way for that thing to have a sign change. Let's do one quick example using the function we have seen before. Okay, now let's find out where on this function is the graph concave upward, where on it is the graph concave downward, and where the inflection points, if they exist, might be. If you want to find out what those things, then those depend on f double prime. Increasing, decreasing depend on the first derivative. Concave upward, downward depend on the second derivative. So we start by finding the second derivative. First derivative is 12x cubed minus 12x squared. Second derivative is 36x minus 24, 36x squared minus 24x. And from this point on, you do the same thing. As if you're finding the increasing, decreasing, local max, min. The only thing different is now we're operating with the second derivative. We're looking for the sign of the second derivative where it might be 0, for example. So we use this function and duplicate everything we've been doing in the last few examples. All right, we make that equal to 0. Factor out 12x. So we get x is equal to 0, and x is equal to 2 over 3. Then we do the same thing, and now we check the sign of f double prime above the chart. Okay, like I said, everything we've been doing is exactly the same with a different function. Okay, choose something in here, plug into here. We will get a positive everywhere. Between here and here, plug into f double prime. This turns out to be negative, and here we get positive. So the function is concave upward here, smiley face. Concave downward, sad face. Concave upward, smiley face. Concave upward is happy. Happy is minus infinity to 0 and 2/3 to infinity. Concave down, sad, 0 to 2/3. The inflection point, IP, at 0, at 2/3. Right? These happen when f double prime changes sign, just like when we were looking for the blank max and min. These will not be the local max and the local min. They're not related to that. They're related to the shape. Okay? But we do the same thing, just with a different function. Okay, that's it for today. Sorry I ran over a little bit. Have a good weekend. See you Monday.